Good morning, ladies and gentlemen. I will change the topic of the case study. I will pass from biology to astrophysics, space physics, and also atmospheric science. I will present briefly, because we are hurried to go to the lunch, the LAGO collaboration and the way in which chain reads helped us to improve our performance on managing all the massive data and the rest of the necessities we have for the collaboration. So this is the roadmap of the talk. I will present the LAGO project, the LAGO detectors, and then I will present the 3 LAGO programs, and the last LAGO program, the virtual program, which is linked with the LAGO chain. But another branch will show you the necessities that we have and how chain can help us. So the LAGO collaboration is the Latin American Giant Observatory of Cosmic Rays, and it is a very long array of water Cherenkov detectors. It is composed by 70 members from 22 institutions at 9 Latin American countries. This is the list of countries, and Brazil is incorporated this year. And we have the main scientific goals, astrophysics particles up to this energy. This energy are very huge energies, but also we are interested on transient and long-term space weather phenomena through the solar modulation of cosmic rays, which is linked with the damages to new technologies in the space and also on ground. Also, we are very interested on the characterization and measurements of the background radiation at ground level. But also we have academic goals, because we are a Latin American collaboration, so we want to train Latin American students in high energies and space weather and astrophysical techniques. We build a Latin American network of astroparticle researchers. So this is the map of our sites of LAGO that range from Mexico to Antarctica, and some of the detectors are already in operation. Some of them are starting in this year, and some of them started last year, and some of them are under evaluation to install in the near future. So I will be fast, so probably I will not describe all the stuff, but just to have an idea of what are our problems. Finally, after all the processes, the physical processes to detect the cosmic radiation, we have a digitalization of the signal, and the time of the pulse that we identify as a particle is of the order of tens or hundreds of nanoseconds, and the number of data is really huge. And we have a time synchronization with GPS in pulse per second to synchronize all the net at the same time. And this is the list of the main devices composing the detectors. And because we developed a very, very important infrastructure to communicate the data to make the acquisition of the data from these particles, we now are developing a new station, which is called a Smart LAGO, water Cherenkov detector, that include also another sensors, pressure, temperature, and another ambient observation from atmospheric science as dioxide of carbon and radiance, etc. And we have this station as autonomous, so we have solar panels and batteries to don't depend of the electricity, of the power on the sites where we locate the detectors. And also we have a GPS connectivity, so just having connectivity from cell phones, we can communicate and transmit the data from our observatory to the central part. So we have several programs. I will briefly describe some of them. One is the Extreme Universe, and it is linked with astrophysics of highest energies of cosmic rays. The another is the LAGO Space Weather. It is based on the study of solar modulation of cosmic rays. and also possible connection with physics of the atmosphere and background radiation of ground and flight level. So in the space, we are interested also in the quantification of the radiation on flights, which is new, and it is part of several Horizon 2020 projects to understand better the level of radiation and the real warning of this radiation on the space. Also, we have a LAGO virtual program to make the acquisition, to produce, to collect, and preserve the LAGO data, the data from our collaboration. And also, we have a human resources formation program linked with the university to attack several problems. These are just examples of the problems that we are using in this program. So I will pass through to one of the program, the space weather program, which is linked with sonar connection, and it is linked with the determination of the radiation transport through several parts of the system, and in particular the cascade that the primary particle produce in the atmosphere when interact with the material of the troposphere. So we have the flux of cosmic rays, and due to the solar activity, we have a modulated flux, and then the modulated flux, because the geomagnetic field produce a deviation and consequence of the trajectories of the particles and the primary particles, and then the atmospheric conditions produce the shower, this cascade during the interaction. This is linked with nuclear physics, and produce secondary particles a lot. And this is one of the problems of the massive data that we have in our collaboration, because the secondary particles are really huge number of particles. And then we obtain the signal in our detector. So there is a synergy between the solar activity and the flux variation of the observed particles. So we have a program of simulations, which is based in Corsica. Corsica is a well-known tool, well-known program, which is used by the community of cosmic rays. For instance, in the Pierre Rocher Observatory, they use the Corsica simulations. And then we prepare a set of different level of simulations. We constructed basically two groups of simulations. This first panel in the left shows the one example of the output of the consequence of the geomagnetic field of the arrival of the primary particles, of the primary energetic particles, the cosmic rays, on the ground. The another one is a consequence of the production of the shower of the millions and millions of particles on ground level. This is a simulations of the interaction of these particles at the detector. So it is linked with the production of the gas of photons in the detectors. And the last one is a consequence of the pulse production to better understand what we are observing. So this is an example of the number of particles in terms of the deposited energy. And you see this is the histogram. This is one of the output of the more important output from our detectors. And we can identify the energy of in each range of energy. We can identify the primary particle. And this is one of the important stuff in our collaboration. This is an example of a Forbus decrease observed in our net. A Forbus decrease is a strong decrease of particles which occurs with the solar storms happen, and this the sun expels a bubble of plasma, and this produces shielding of particles in the around of Earth. And this is the modulation of the particles on the term of 10 days or something like this. And you see that there is a strong decrease and the recovery of the particles. I will skip this. I will just show that we are developing teaching in the university, and then I will pass to the LAGO Virtual, which is illustrating the massive data production. We have a raw data of 1 terabyte per year per detector. And we also, because our plan of simulation, we produce typically 3 terabytes per year per site, because we simulate in different way each site, because the different conditions of the atmosphere and different conditions of the geomagnetic field require us to simulate in each site a different simulation in our net. And then we are deploying a LAGO Corsica implementation on the European grid, and we already got success on this implementation. And to the connectivity of different sites, we use Red Clara in Latin America. And also, we have at the moment a data repository located at Colombia. And using the Red Clara, we transfer the data from each site to this repository. So our data generators are the sites, and then we produce a curated raw data, and through the help of Chainred, we can produce a cloud, a curated, pre-processed, and processed data, and this is available to the members of the community to can access to this raw data, and we, in the near future, we will open all our data to the community, to the public in general, because our idea is that the data are open. We are developing also searching machine to locate the different data, because the number of data is really huge, so it is impossible to get the proper data if you have not a sophisticated engine to make the search. Okay, this is the another step because we have applications on the curated data. So we have also a set of tools to obtain different aspects of the data. And this is okay. Chainrace helped LAGO, helped us in adoption of standards and data infrastructure, including metadata organization, permanent identifiers for the data files, data accessibility. Chainrace has helped LAGOs to configure and turn up this open accessibility data and repository. Now we are integrated in the Chainred, KB, and SSE. And finally, it is two pictures of the front end that we developed in LAGO to can access to the European grid and to run Corsica, which is our main computing demanding simulator, using this grid. And I think that's all. So let me just to summarize and conclude. Ultra-long baseline array of smart water Cherenkov detector from Mexico to Antarctic, high and low latitude sites across the Andean range. We identify background radiation, space weather, and high energy phenomena, and we developed a new smart device and environment stations, and the data are open to other communities, mainly environment station, which is more common to find researchers in these branches, and a full simulation of change from primary flags to the signal of detectors are developed in the collaboration. And LAGO simulation program started to develop the Corsica grid version, and LAGO is now integrated to the chain range KB SSE. Thank you very much for your attention.